Hello. My name is Patrick Jobin, and welcome to my Growth Hacking with Confidence Intervals webinar. It's a little workshop that I put together for marketers and people with startups to want to take their startups to the next level and try to take risks and quantify some of the risk out of taking sort of bigger leaps in their business. And first, we'll look at the example of Alfred. Has a startup. He's got a good reputation. He's been growing organically for a couple of years. His customers love him, but he's kind of hit a bit of a wall in his business, and he wants to really take over the market. He wants to turn his business into sort of a major player in the industry. And in order to do that, I think he's found a really good opportunity to accomplish it. As I said before, let's lay out our problem statement. So Alfred wants to take his company to the next level. However, he must ask investors for substantial cash infusion. There's a partner in his industry that has the ability to give him 2,000 leads. However, it will cost $70,000, which comes to about $35 per lead. Alfred did a little bit of due diligence, and he found that these leads would be of equal or greater quality to another lead source that he has access to that would offer leads at $120 per lead. Another drawback of these a la carte leads would be that they would be lower volume. So you could get maybe a few leads a day at most from this source, whereas the 2,000 leads would be sort of in a bigger chunk, much higher volume. Another thing complicating Albert's decision is that his sales cycle is sort of medium length. It's about 3 months. So when he gets a lead, he typically won't know on average until about 3 months after if he's gotten the lead. So he's lacking the instant feedback when he buys these leads. He has to sort of work it a little bit. So so this raises a good question. How does Alfred demonstrate the feasibility of his plan to investors while also quantifying the risk that they would be taking? So let's sort of design an experiment that would help Alfred lay this out. Alfred would be simulating a $35 cost per lead with a target cost per acquisition of blank. So he's got some maximum in his head for what he's willing to pay to obtain a sale within 3 months. And we're going to lay this out as sort of a threshold, a maximum cost per acquisition threshold on a graph. And we're going to create a hypothesis. Now, hypotheses, you do not prove hypotheses, you disprove them. So we have to create a disprovable hypothesis. So in this case, we will create a hypothesis that the average cost per lead is too expensive for the conversion rate, or the conversion rate is insufficient in order to ensure an appropriate cost per acquisition. So that's what we're going to be sort of hypothesizing here is the average cost per acquisition is higher than the maximum threshold that Alfred is willing to pay. So here we've got a few examples from some samples that we might take. So we would be paying a much higher price. So let's skip to that part later. But first, let's talk about sort of the methodology. So let's suppose that we take a sample, and the sample has a certain mean cost per acquisition or certain mean conversion ratio. And we're going to take the mean and also the 90% confidence interval. So why do we go through all this trouble of calculating the confidence interval around the mean? Well, confidence intervals are useful because as as the sample size gets larger, then the confidence interval shrinks, and as the sample size gets smaller, then the confidence interval gets wider. And this is really useful because it means that we can make sort of more definitive decisions based on smaller sample size. Or in Alfred's case, it means that we'd be able to conduct the experiment at a much lower cost and get results much faster, which is good because it's good to move fast on important decisions. So here's three examples of how the experiment might go. One example is the mean cost per acquisition is below the threshold, and also the confidence intervals are also below the threshold. So in this case, we would reject the null hypothesis, and we would say that there's at least a 95% chance that this deal would be successful. Then there's this situation over here where both the mean and the confidence intervals are above the threshold, and in this case we cannot reject the null hypothesis. We have to assume the cost per acquisition would be too expensive for Alfred. However, there's a third situation over here where the mean is below the threshold for the sample. However, the confidence interval overlaps the threshold. So in this case, even though the mean is below the threshold, we cannot have a good enough degree of certainty that the experiment would actually provide a positive result. We cannot reject the null hypothesis. So in this case, we have two options. We can either sort of reject the experiment, say it was a failure, or we can collect more data. And by collecting more data, one of two things might hopefully happen. One is that the confidence interval will shrink to the point where it's below the threshold, or the mean might move this way a little bit, and we could finally reject the null hypothesis. Um, it would be one or the other, or possibly both of these situations coming together. So what do we mean by null hypothesis? So let's define that a little bit. At $35 per lead, the cost per acquisition within 3 months will be more than $465. That's the null hypothesis that we're designing. Where does this $465 figure come from? Well, Alfred knows that he has a maximum cost per acquisition of $500. He cannot afford to pay more than $500 to obtain a customer. And then he subtracts $35 of inside sales call time, which is what he estimates would be required in order to convert one of these leads into an account or a deal within 3 months. The experimental cost per lead in this case will be $120, which is much higher than the theoretical cost per lead of $35. So we will be using the a la carte leads as a proxy for the $35 a lead, because we cannot purchase that yet. We don't have the capital, and that's really the purpose of this experiment. So we will be measuring, instead of cost per lead, we'll be measuring conversion rates in we'll sort of go over that a little bit later, but instead of measuring the actual cost per acquisition, we'll be trying to quantify how many deals can we get for X number of leads, and that's really how we're going to be defining it. And then we can sort of abstract it back to the $35 mark afterwards. So in order to reject the null hypothesis, the mean cost per acquisition plus the right tail interval has to be smaller than the threshold. So let's look at this in action. So here we've got a 90% confidence interval. And one thing that's interesting is over here, if we had a situation that was the opposite of this one, where the mean was higher than the threshold for the null hypothesis, but the lower tail overlapped the hypothesis into the rejection zone, we would still fail to reject the null hypothesis. So in other words, the lower tail is completely useless. So we can actually get rid of it. And now we have a 95% confidence interval. So in this case, we have 95% certainty that if we tried this experiment on a larger scale, that it would provide a result that was below our null hypothesis threshold. So a 95% chance that we could reject the null hypothesis on the large scale in the population as well as in the sample. So in this experiment, we'll only be doing sort of a right tail test, or we'll only be looking at the right tail of the distribution in order to create our confidence interval. So once again, here's our parameters. So our confidence interval is going to be 95% right tail only. Our cost per acquisition is going to be, well, it's 5% right tail, so it's 95% left tail. Sorry. Our cost per acquisition that we're targeting is $465, and our cost per lead theoretically is $35, which means that we should aim at a conversion rate of about 7.5% for our experiment. If we can get these $120 leads to convert at a rate of 75%, and we can show that this will happen if we apply the investment, then this would be a feasible business deal for us, a feasible opportunity. Once again, we want the number of deals represented by lambda plus, so basically the confidence interval is the number of deals represented by lambda plus some sort of the t-value, which is the 95% interval with lambda minus 1 degrees of freedom. Remember, lambda is just the number of deals that we're getting. times the square root of lambda, times the square root of the number of deals we're getting. And this is sort of like the mean plus the confidence interval. And we take that, we divide it by the total number of leads that we purchased. And so how do we run the experiment? One possible way would be to just purchase leads until you get a certain number of deals, right? And this makes sense because we're using a Poisson distribution. In a Poisson distribution, lambda is what determines the mean. It's what determines the standard deviation. It's what determines the standard error. So it's really, if you base your entire experiment on lambda, that's how you should get the most practical results and the most accurate results and the most control over your experiment. So for example, let's say you purchase leads until you get 20 deals. And then you go back and say, okay, I've got 20 deals now. Let's look at how many leads I had to purchase. And you go, oh, if I had to purchase more than 215 leads, then the experiment was a failure. And if I purchased fewer than that, then it was a success. There's a problem with this approach. In this case, the sales cycle is 3 months. So and also there's a low volume for the $120 leads. So the experiment could go on for a very long time as you wait for the leads to drip in, and you won't know for at least 3 months if you've purchased enough leads. So you could just end up spending and spending and spending just out of control because you have to wait. You don't know, you don't have this threshold for when you've purchased enough leads. So this is really not the ideal solution in this case. Another alternative that I would propose is to take the ratio of the deals divided by the number of leads and to check to see if that falls within our confidence, that falls above our within our confidence threshold. So in this case, we're looking for a 7.5% conversion rate, which is represented by the blue line, plus our conversion ratio threshold, which is represented sort of over here by the red line. So here we just purchased a certain number of leads. Let's say we're going to purchase 400 leads or 200 leads. And then after 200 leads, we look. After 200 leads, is it, did it convert at over 10.5%? If the conversion rate's over 10.5% after 200 leads, you have 95% certainty that this deal will work out for you. But what happens if you don't meet that threshold? What happens if you're down here? Well, then you might make a decision. You might think, okay, do I collect more data? Did it fail because I didn't collect enough data? Or did it fail because the experiment is just not going to work? I cannot reject the null hypothesis. That depends. If you're over here, then it might make sense to collect more data. But if you're way down here, then at least you know early on, no, this isn't going to work out for us. And you have to be a little bit careful, especially if you got a lower conversion rate. You have to sort of be careful with the number of deals that you're bringing in, because, well, never mind. So let's look at this formula again. So the number of deals is a different variable than the minimum number of deals that you need to obtain, than lambda, right? These are two different numbers. However, the number of leads is identical to n. So since these two, because these two are the same, then we can actually simplify this to ask the obvious question: is the number of deals greater than the minimum required number of deals plus the confidence interval? And that's really what we're trying to ask, and it can be simplified into this formula over here. Also, the cost of the experiment. What's your budget for this? So the way you determine the cost of the experiment is you take the number of leads times the cost per lead, and that will tell you the total cost of the experiment. So you can set a limit for how much you're willing to pay to find out this information. So this works for 3-month cycles. So another thing that's important to keep in mind is when we say we're measuring, after 3 months, it's not after 3 months of starting the experiment. This is cohort. So you're buying leads, you're sticking them in the cellar, you're waiting for them to ferment, and then after 3 months of sort of being in the cellar, you wait to see, oh no, is this a vintage quality lead? Did this convert into a sale? So when you're evaluating after 3 months, it's after each lead turns 3 months old. It's the first 3 months of every lead's life. So you don't measure things that happen 4 months later. You don't measure things that that happened 3 months after you started the campaign, but now you've purchased the lead in month 4. that you do not count. You only count as a cohort the leads, what happened in the first 3 months of that lead's life. It's very important to make that distinction. Now, why am I talking about cohorts? Well, what happens in the case of longer sales cycles? What if your sales cycle is 8 months, a year, 2 years? Well, in that case, it might make sense to create many daily cohorts. So it's a bit more work, but you create maybe one cohort for 365 different days. And then based on this cohort, you can actually plot a regression line and get a pretty good estimate of what your conversion rate will be after a year, or what your cost per lead will be after the period of 1 year. And that might allow you to shorten the amount of time that you wait before you get a result, before you figure out whether or not you want to jump on this opportunity. But it has to be something close to a year. You can't just take 2 weeks worth of results and then extrapolate that out to the year, because you're not going to get a very accurate result. So you still do need to do a significant portion of that time period if you're going to be using regression to solve this problem. And the result will not be terribly accurate. That's something you have to keep in mind. So that's the end of my presentation on growth hacking using confidence intervals. Thank you very much. If you'd like to play around with the spreadsheet that I used to create this, you can actually access it. I have made it available in a link in the comments. And also, if you would like to take a look at the presentation yourself and sort of play around with it, I've also included a link to that in the comments. And if you'd like to sort of get to know me a little bit more, you can visit my website at rickjobin.com. Thank you very much and have a nice day.